Hello. So today we're continuing with our work and energy outline, and today we're going to talk about the dot product. Okay. Now the dot product is one way to multiply. Okay. Now normally we think, okay, there's only one way to multiply, but there's actually two different ways to multiply when we're talking about vectors. Okay. So dot product is one way to multiply vectors. There's also such thing as cross product, right? In math, you often see like 1 times 2, right? And so this dot represents multiplication, but you could also write 1 cross 2, right? And these two things are the same. But when we're talking about multiplying vectors, they're actually different, right? So the dot product is going to be different from the cross product. Here, dot, and here, cross, right? So they actually give us two different things, okay? So a dot product is actually the same as what we're doing when we're doing work. So we have work, and this is sort of our general definition of work. And so another way you can actually write this is F dot D, okay? And so the reason I'm putting this line above here is that represents that F and D, since they both have this arrow here, are vectors, okay? Another way you'll see it in print, like in the textbook, is by bolding it, okay? So by putting a bold here, we're representing that F and this D are vectors, okay? So sometimes you'll see it bold, sometimes you'll see a little arrow, sometimes you'll even see just like a full arrow at top or the half arrow. But that's just saying that it is a vector, okay? And then when we have this dot, it's saying we're going to take the dot product of these things. So, some formula sheets may actually specifically define work as F dot. Okay? So let's go ahead and dig a little bit further. Okay? So, as we kind of already talked about, the things you can multiply, it has to be vectors. Okay? So, we're starting with two different vectors, not a vector and a scalar or two scalars, specifically two vectors. Okay? And then the result is actually going to be a scalar. Okay? Now this should make sense because we know that energy is scalar, not a vector. Okay? And so just like this, when we multiply two vectors, work, F dot D, okay, we actually get a scalar. Okay? Because we know that work is just a number. Okay, it does not have a direction, whereas force and distance both have a direction. Okay? So before we can actually explain how to find a dot product, we actually have to look at ways to represent a vector. Okay? So far, the only ways that we have actually represented a vector is just by writing the magnitude and the direction. So for example, force equals 1 Newton north. Okay? And this is fine, but sometimes it's actually more helpful to use some different ways to represent that vector. Okay? So one way that we can represent a vector is very similar to sort of points, coordinate points. So this vector here would be something like 0, 1. Okay? Right? That's the coordinate system. So if I just draw a graph, right, I want to go up 1, right? So that would be 0, because my x direction is 0, and then 1. Okay? If I want to show that this is a vector, instead of using these parenthesis marks, I'm going to use brackets. So this kind of thing. Okay? Greater than, less than sign, basically. But 0, 1. And then I'm going to put another comma, because in physics, we often have to deal with 3 dimensions, not just 2 dimensions. Okay? And then my third dimension, so obviously I have x, right? Then I have y, and then my third dimension is into and out of the board, which is z. Okay? You'll also see it as like a circle with a dot or a circle with an x. Okay? And so since it's just north, that would be something like this: 0, 1, 0. Okay? And so this is just this vector here, where it is 0 in the x direction, 1 up, and then 0 in that into and out of the board space. Okay. Now, could represent other vectors with this as well. So you could also do something like 5, 4, 10, right? So 5 in the x direction, 4 in the y direction, and 10 in the z direction. Okay? So that's one way we can represent vectors. But there's also another common way that you will see, okay? Where instead of putting these commas here, we use a different thing to represent the x, y, and z directions, okay? So the way we write this is with 2 I hat plus 3 j hat plus 4 k hat, okay? So this I hat represents the x direction, okay? This j hat represents the y direction, and this k hat represents the z direction, okay? So this would be 2 in the x direction, 3 in the y direction, and 4 in the z direction. Okay? And so that's just one other way. So I hat itself, that would be equal to a vector that is 1 in the x direction. Okay? J hat would be 1 in the z direction. Sorry, J hat would be 1 in the y direction, and K hat would be 1 in the z direction. Okay? So it's actually very similar to this, right? But here we're just using slightly different terminology. So the thing that to remember is I hat, or this first part here, is in the x direction. J hat, or the second part here, is in the y direction. And then K hat, or this third part here, is in the z direction. Okay? So, finally, how do we actually find this dot product, right? So we now know how to represent vectors, okay? But how do we actually find that dot product, okay? So I'm going to go ahead and erase for a second. We know that we're going to get a scalar answer, okay? So we're going to end up getting completely rid of this, or completely rid of this. And we'll end up with just a number, okay? Without any direction. So, let's say I have something like this. So let's say I have 3, 0, 0, dot, 4, 0, 100. Now, before I actually get an answer, we want to talk about what the dot product is doing. Okay? Now, we already know work, FD cosine theta. We know that this is a type of dot product, right? And we know that when we're trying to find work, if I take this away, right, I want to know how much are these in the same direction, right? For example, we know that if they are perpendicular, right, my force and my distance are perpendicular, my work will be 0, right? And so the dot product is really asking how much are these two vectors in the same direction, okay? If they're not in the same direction at all, I get 0, okay? If they're in opposite directions, so like this and this, you get a negative number, but you will still get a number, okay? But if they're in the same direction, okay, then you end up with the biggest possible number, okay? And so when we're looking at this here, the actual mathematics isn't very hard. All I got to do is multiply the first two numbers, so we get 3 times 4, plus the second two numbers, 0 times 0, plus the third two numbers, right? The third numbers, 0 times 100. Okay? So this just equals 12 plus 0 plus 0 equals just 12. Okay? So it's actually mathematically pretty simple to be able to do this. Okay? So another example, let's say I have 2I hat plus 3k hat dot product with 4I hat plus 6j hat plus 0k hat. Okay? Now this one's a little bit trickier because it's just missing that j hat. Okay? So you could actually rewrite this vector here as 2I hat plus 0j hat plus 3k hat. That would actually be the same thing. And so when I go ahead and do my dot product, I need to be thinking that this is a 0j hat. Okay? So I multiply my first two numbers, 2 and 4, 2 times 4 plus my second two numbers, which this one is just 0 because it's not there. So it would be 0 times 6 plus 3 times 0. Okay? And so that's my dot product there. So this will equal 8 plus 0 plus 0, so just 8. Okay? Now sometimes if you have it filled out with numbers, you'll get a bigger number because we won't have these zeros. But the reason that these zeros kind of cancel this part out is because we're looking for the part that they're in the same direction. Okay? Because this one has a 0 here, it's not in that z direction at all, even though this one is, so that part goes away. So finally, what is the dot product formula for work? Well, we kind of already showed this a little bit. So it's just work equals F dot D. I want to represent that these are two vectors. Sometimes when it is a dot product, you'll see a bit of a bigger dot, not just a little dot, but a little bit of a bigger, almost like a bullet point kind of dot. Okay? And then you have some practice problems here with a link to the answers at the bottom. Once again, if you are stuck, if you need some help, feel free to send me an email and let me know.